Okay, hello everyone. The topic of my presentation is lifetime of titanium alloys under consecutive dynamic and very high cycle fatigue loads.
Could you use the slideshow mode
Uh,
at the lower?
okay.
Yeah,
Okay,
thank
now
you.
we can see your
Okay.
presentation in full
Uh-huh.
screen. Thank you. When you want.
Thank you. Mhm. The influence of random statistic and dynamic loads on the lifetime of materials under very high cycle fatigue is the considerable current interest as to reliability of estimating the strength of aircraft motor materials under real operating conditions. An example is the estimation of the endurance of gas turbine engine blades under the collision with solid particles, what's usually called as the foreign object damage. In this work, we investigated the influence of consecutive dynamic and very high cycle fatigue loads on the lifetime of titanium alloys VT6 and VT8. The relevance of the problem statement is determined by the critical applications, life estimation of materials and structural elements of aircraft gas turbine engines, expressing random dynamic effects under flight cycle conditions. Dynamic preloading of titanium alloy specimens was realized using the split Gopkinson pressure bar setup, after which the specimens were subject to cyclic loading. Here you can see the split Gopkinson pressure bar setup. It's shown how the specimens are installed between the rods and specimens after the testing. Fatigue tests were carried out using the resonance type of testing machine of Shimadzu USF 2000. This machine provides 10 in power 9 up to 10 in power 10 loading cycles with the amplitude from 1 to several dozen of microns and frequency of 20 kilohertz, which reduces the testing time in the comparison to the classical fatigue testing machine. The cooling of the specimens was realized by compressed air. This slide shows the dependencies of the stress value on the lifetime to failure after dynamic preloading. It has been found that the fatigue failure stress of the preloading VT6 titanium alloy decreases from the steel stress level of 460 megapascal to 130 megapascal, which corresponds to a critical number of cycles, 10 in power 8. It was found that the limiting fracture stress of the preloading VT8 alloy decreases to 65% from a stress level of 571 megapascal in the initial state to a stress level of 200 megapascal, corresponding to a critical number of cycles 10 in power 8. This slide shows characteristic surface relief of a fatigue fracture zone for high and very high cycle fatigue. For the specimens subject to cyclic loads in the range exceeding 10 in power 8 cycles, the crack formation is started inside of the specimen. The fracture surface in this case exhibits a fatigue zone known as the fisheye, which is a particular feature of such fatigue regimes. The center part of this region comprises a fracture nucleus surrounded by the region of submicrocrystalline structure. We used the new view interferometer profile of high structural resolution for qualitative fracture surface analysis, which provided the data allowing us to find correlation between mechanical properties and scale invariant characteristics of damage-induced roughness formed under high and gigacycle fatigue loading conditions. The approach to characterization of a fracture surface morphology in terms of spatial invariance was proposed by Zeiser and Bouchot. The function k of R is calculated for one-dimensional profiles of fracture surface relief according to the formula 1, where k of R is the average difference between the values of surface relief heights and h is the Hurst exponent. Representation of the function k of R in logarithmic coordinates allowed one to evaluate the lower boundary of scaling range L mean and the value of our boundary considering one as the characteristic scale of process zone L max. That's the area of correlated behavior of multi-scale defect structures. A comparative analysis of scale invariant characteristic of specimens made of titanium alloy VT6 in the initial state and after high and gigacycle fatigue loading allowed us to establish the constancy of Hurst index 0.6 in a wide range of spatial scales of 0.8 up to 47.9 microns in figure 11. We use special scales for writing the kinetic equation for the crack growth. The kinetic equation for crack growth dl our dn is the function of phi of stress intensity factor, Young modulus, and L scaling correlation scaling the ensemble of defects, and LPZ, the scale related to the process zone. Dividing both sides of kinetic equation by L scaling, we have similar the Paris law, formula 3, where alpha is a universal exponent. The function k of R in logarithmic coordinates allowed one to evaluate the lower boundary of scaling range L scaling and the value of upper boundary considering one as the characteristic scale of a process zone LPZ. That's the area of correlated behavior of multi-scale defect structures. And finally, the results are given in these slides. It has been found that the fatigue failure stress where preloaded VT6 titanium alloys decreases from the stress level of 460 megapascal to 130 megapascal, which corresponds to the critical number of cycles 10 in power 8. And it was found that the limiting fracture stresses of a preloaded VT8 alloy decreases to 75%, corresponding to a critical number 10 in power 8 cycles. And comparative analysis of scale invariant characteristics of specimens made of titanium alloy VT6 in the initial state and after high and gigacycle fatigue loading allowed us to establish the constancy of the Hurst index in a wide range of spatial scale. And these results confirms our assumption that mentioned characteristic scales, LPZ and L scaling, play an important role in the list of variables for kinetic equation fatigue crack growth and can be used for the identification of phenomenological parameters providing self-similar law for the crack path. And thank you very much for your attention.